Okay, so we discussed that the velocity is basically the differential or derivative of the displacement time graph, and we drew the graph for the velocity time graph by using the gradient thing. Okay, and and now we have to work out for the equation of the velocity time graph. Okay, now let's see how it will be. So we can say that. mm, okay. So we can say that the velocity, sorry, so the velocity is basically equal to V naught. Can you tell me which mathematical function is this one? Is it the
The
cos
what?
one or the sine one?
Cos.
Cos, very
Or
good. Okay, so you are saying that this is the cos function. Okay, so V naught and then cos omega t. Okay, so this is the graph or this is the relation for the graph. Okay. And if we try to differentiate this equation, right, like the previous equation, so the differentiation of that equation gives me the equation V is equals to x naught omega cos omega t, right? And you have learned this formula in simple harmonic motion that the maximum velocity or the velocity, the tangential velocity is basically r omega, right? So over here is just a bit replaced with this formula. Okay.
Okay. Sir, can we take omega as a common between like,
No, we can't because over here omega is inside the angle, right? And inside the angle things cannot be taken out, right?
okay.
Okay. So yep. So so by the way, this formula is for the maximum velocity. Okay, maximum velocity, and always keep in mind this formula is very important. Okay, always keep in mind that. So this formula is very important. Now, so this is the concept for the velocity. Okay, and if we talk about the acceleration, by the way, we also discussed that the velocity will be zero at the end and will be maximum in the beginning in between. Okay, now let's talk about the acceleration. So the graph for the acceleration look like. Mm, wait. So the acceleration. Okay. So, so the concept of acceleration in simple harmonic motion is um, going to be the rate of change of velocity. Okay, the rate of change of velocity. Okay, and the rate of change of velocity is basically um, dv over dt, right? Over dt, right? Now, to relate this concept, we again have to copy paste the whole thing. Okay, and okay, let me just take this thing out and let's just paste it. So copy and paste. Okay. So so since we have to consider the velocity time graph while making the acceleration time graph and acceleration time graph basically depends upon all of the thing, right? When you have the referential displacement time graph and the velocity time graph, then you can make the acceleration time graph accordingly, right? Like you cannot make it on its own, otherwise it won't work. Okay, so let's make the acceleration time graph. Okay, okay, so just continue the lines, continue the lines. Okay, and okay, fine. So if we consider, can you tell me which property of the displacement time graph gives me the velocity time graph, acceleration time graph?
What?
If I want to make the acceleration time graph, okay, so which quantity, like the gradient or the area, give me the acceleration time graph?
The gradient of the.
Very good. So you're saying the gradient of the displacement time graph, oh sorry, the gradient of the velocity time graph gives me the acceleration time graph, right? So now let's try to make the gradient of this graph. Okay. So over here in the starting, the gradient is zero because if you make the tangent, so tangent is horizontal, right? So initially the gradient is zero, right? The gradient is zero, and then gradient is maximum when the velocity is zero at this point because when you draw it, so it is maximum, but in the negative direction. So uh just make right here, and then it is zero at the maximum velocity because the gradient is the horizontal, the tangent is horizontal, right? So it will be right here, and then it will be right here, right? The velocity will be maximum, and then like this. Okay, so the velocity time graph looks like this. Sorry, not the velocity, the acceleration time graph looks like this. Okay, so this is the acceleration time graph. Okay, and can you tell me which function is this one? Yes,
What's up?
which function is this one? Is it the sine function or the cos function?
It's a sign. Yeah.
Okay, negative sign, positive sign.
Negative. Yeah, because
Very good, very good,
it's
because
also.
it's starting from the opposite direction. Okay, and the maximum acceleration is right here. Okay, and the minimum acceleration is right there, or the negative maximum acceleration in the opposite direction, right? So if we try to make the equation, so the equation will look like acceleration is equals to a naught, and we have
P minus sign?
negative,
Or
yes, negative
yeah.
sine omega t, right? Now you should remember that, or you have to remember that the maximum acceleration, okay, a naught is basically the maximum acceleration. Okay, so this is the maximum acceleration. Okay, maximum acceleration. Okay, so this is the maximum acceleration. Now, if we talk about the concept of the maximum acceleration, so it is basically, it has a formula a naught is equals to x omega square, right? Previously we did this with r omega square. Okay, a is equals to a is equals to r omega square was the acceleration or the centripetal acceleration, right? And over here, x naught omega square is basically the acceleration, the maximum acceleration of the pendulum, right? So this is the formula for the maximum acceleration. Very useful equation. Okay, they'll ask you a lot of times, so be very careful. Okay. Okay.
Yes.
And if we try to draw the graph for the two equation, right? This one and previously that one. Okay, the x naught omega and over here this one. Okay. And by the way, if I make the pendulum right here, okay, so you can see that initially, In the pendulum, the velocity, sorry, the displacement was maximum right here, okay? And maximum, the velocity was zero, okay? And the acceleration was negative maximum, right? And over here, the displacement is zero, okay? The velocity is maximum, okay? And the acceleration is also zero, right? And over here, the displacement is maximum, but in the opposite direction, right? The velocity is maximum. Sorry, the velocity is zero because of the max height, and the acceleration will be maximum, right? So you can say that, or you can see that the displacement and the acceleration are both be maximum at the same time and zero at the same time, but they are actually in the opposite direction, right? So where the displacement increases, the acceleration increases in the opposite direction, right? Or the displacement decreases, the acceleration decreases in the opposite direction, right? So this is the concept, by the way. Now we have to consider that, if this is the case, we have to consider that how the force act, or before that, let's just draw the graph and then we'll move on to the forces, okay? So let's say if I want this graph, velocity is equals to x naught omega, okay? And I want to make this graph acceleration is equals to x naught omega square, right? So I have these two concepts and I want to make the graph, okay? So can you suggest the shape of the graph, please, for the first function?
Inversely, so it's inverse here.
Invert x again. Wait. Mm, so if I have x in centimeter, or you can say that in meters, okay, and velocity in meters per second, right? So how it is inversely proportional, and to which quantity does it inversely proportional with?
Uh, in
It
the
is.
opposite side, I
Hmm?
think.
Actually, it is basically, in this case, it is basically constant. It is basically directly proportional velocity and amplitude. So if you try to draw the graph, the graph would look like this. Clear?
Yeah.
Perfect. Okay. And the gradient of the graph is basically is equals to angular frequency or omega. Okay.
That's,
Now, so these are the maximum values, by the way. Okay, these are the maximum values, right? Now, this is the velocity, and for the acceleration graph, for the acceleration graph, it would be okay. And this graph is like a very common. A naught A in meter per second squared. Okay. And over here we have the displacement. Okay. In meters, right? Now, can you predict the shape of the graph? And keep remember that there's a negative sign as
yeah,
well.
so
Hmm.
would it be like two curves? Like, um,
Like this and that.
yeah.
But that is the case when you have something inversely proportional. Like when you have A is inversely proportional to X, then this sort of thing will come out. But for now, this won't be the
Would,
case. This isn't the
would it
case.
be
Hmm.
the same but on the other side, like
Hmm.
directly proportional but on the other side?
Yes, very good, very good. So it would be over here, right? This. Okay. but you have to make sure that, or if you're not drawing it, or you're not given in the paper, then fine. If they give you in the paper, then you have to make sure that these values should be same. The starting value, okay. Okay, so these should be their acceleration and the maximum velocity. Okay, so this is the acceleration. This is the maximum acceleration. This is also the maximum acceleration, but in the opposite direction. This is the displacement, and that is the displacement as well. But over here, it will going to be positive, right? So now you can see that the acceleration and displacement are oppositely directed. Okay. Now let's talk about. Okay, so this is done. Okay. Now we have one more relation, and that relation is basically the velocity and the displacement relation. Okay, in the pendulum or in the motion. Okay, it's also very common, very, very common. So the relation, okay, by the way, over here in the second graph, gradient is going to be omega square, right?
Yeah.
Okay, now if I have the displacement and the velocity relationship, okay, so displacement and velocity relationship, okay. So the displacement and velocity relationship is like very simple. Oh, you only have to remember the main formula, okay? While the main formula will also be given in the exam, okay? But the formula is V is equals to V is equals to X naught. We actually have the equation V is equals to V naught cos omega t. Come on, cos omega t, okay? And you can replace V naught with its formula, and that is X naught omega, okay? X naught omega cos omega t, okay? Now, after the substitution, we will get this form, which you remember it and which you should know how to use it, okay? And the form is basically V is equals to plus or minus, and then we have x naught squared minus x squared, okay? So x naught is basically the position, sorry, the amplitude, and x is basically the position at any instant of time, right? So these are the 2 points, or these are the two things that we should remember, okay? Come on. Okay, so this formula is like very important. They ask you a lot of time in the exams. Okay, so be very careful. Now we have one more thing, and that is the graph for this function. Okay, so if we look at the graphs, okay, so the graph will look like this. Okay, okay. Now come on, I should draw this line so that it work properly. Now the relationship between the velocity and the displacement, or the position and the displacement, is basically more like elliptical, okay? And it's not from the complete circle, it's from the elliptical shape. And over here we are using that one. let me just explain it a bit. Wait, sorry, it's not that correct. Okay, come on, I can move it. I can. And we have right here. Okay, so this is how the graph looks like. Okay, when the maximum point on the y-axis is going to be the velocity. Okay, and the minimum point is also going to be velocity, but in the negative direction. And this point is the displacement, and that point is also the displacement, but in the opposite direction. Okay, so but by the way, this formula is like very important. Okay, and they ask you like many time this formula in the exams. Okay, so be very careful. Now we have to analyze the simple harmonic motion with respect to the forces. Okay, but before that, just give me a minute. I'll be back. Okay. Okay. One last thing, and that is the force analysis of the simple harmonic motion. Okay, and this is going to be the last thing for this portion. And then in the next portion, be doing the energies, and then we'll be done with the chapter. Okay, so um, so this is going to be the force analysis. Force analysis. Okay, now, okay, so in force analysis, you again have to consider a simple harmonic motion. Okay, and okay, let me have my pendulum back. Okay, so this is my pendulum. Okay, let's just give this a pink green color. Mm, okay, now, okay, so this is my pendulum. Okay, and the pendulum is moving, right? So initially, if the pendulum like initially when the pendulum is at its mean position, so the downward force which is the weight should be equal with the upward force, right? And that upward force is going to be tension in the spring. Okay, tension in the spring, right? And at that point, both the forces will be equal and no resultant force will be there, right? But at any angle, so let's imagine that we have this angle, or you can just ignore this thing, okay, and just drag it to the other side, okay. And if I have this side having the angle theta, okay, and if I try to make the forces, so this is going to be the weight which is constant, right? Which is constant, right? But the tension now will be in this direction. Okay, it will be in this direction, T. Okay. Now, if we try to make two component of the tension, so first is going to be in this direction, and the second is going to be in that direction, right? And the first one will be T. The horizontal one will be T sine theta, and the vertical one will be T cos theta. So T sine theta and T cos theta. Okay, T cos theta, right? So T cos theta is basically get balanced with weight, okay? But T sin theta is in balance, okay? So we can say that T cos theta is equals to weight, okay? So no resultant force in the vertical direction, okay? So this is the first thing. But there's a force T sin theta, and that is unbalanced. T sin theta, this force is unbalanced. Okay, and that brings MA, the resultant force, gives me the mass times acceleration. Okay, so horizontal force is unbalanced, uh, causes the acceleration in the system. Okay, and you can say that, yeah, I'm ending in 5 minutes, don't worry. Okay, and you can say that since T sine theta is equals to MA, and A is also, we derive the equation for A, so sorry, T sine theta is equals to M, and A is basically the negative x naught and then omega squared. Okay, so you can see that T sine theta is equals to minus M x naught omega squared, right? You probably learned this thing in the circular motion that F is equals to F is the resultant force, okay? provides the centripetal force. So mr omega square. So in place of m, we are using x. So yep. And this basically this formula shows that force is directly proportional with the displacement, but they are oppositely directed. Okay, and force is inversely proportional with the displacement, but they are oppositely directed. And this is the definition for the simple harmonic motion. Okay, let me just add this definition in the beginning. It should be in the beginning. Okay, I'm just adding one more thing, and then we'll be ending the class. Okay, so simple the definition of the simple harmonic motion is something that I want to add. Okay, now so basically right here. Okay, so simple harmonic motion is basically the motion the motion in which force is proportional. Force, you can say that force or acceleration is proportional to displacement, and both are oppositely directed from the mean position. Okay, so this is the definition of the simple harmonic motion we have right now. That's it. So we have done the concept of the simple harmonic motion and all of this stuff. Okay, in the next class, on the next week, we'll be doing the remaining the energy concept of the simple harmonic motion, and then we'll move on to the questions. Okay, but for now, that's it. Okay, channel. Okay, take care, guys. Love is. Harmonic motion.